So with this, again, we switch to the next talk by Erin. Erin, do you mind switching to the next, sorry, to
Yes.
share the slides here. Thank you. Thank you.
You should see the slides now, right?
Yeah, I can see the slides. So our next speaker is Erin Held, and he'll be talking about black holes beyond general relativity, shadows, stability, and nonlinear evolution. Erin, over to you.
Yeah, thank you very much for also to Sriram and the other organizers for bringing us together in this virtual way. And I think we all agree that it's an exciting time for general relativity, but also for black hole physics in particular. Mainly because, as Anuradha so nicely talked about, LIGO, but also the Event Horizon Telescope collaboration, they provide us with new data, not just in one, but actually multiple different ways. And so hopefully we can learn both about from these shadow observations that probe actually just the background space-time, and from gravitational waves, both in the linear and in the nonlinear regime of evolution of general relativity or some theory beyond. And so it's really up to theorists to keep up with this amazing experimental progress. And that's exactly what my talk is going to be about. And in particular, this means that I think we now have to go beyond just null tests of general relativity and somehow figure out how to make predictions for leading order corrections or some modifications beyond general relativity. And so I want to start with a brief theorist's overview of black hole phenomenology, especially in effective field theories, EFTs, beyond general relativity. And I want to highlight that there's a first question, whether you want to take into account ghost modes or not, or in which way you take them into account. Because whenever you truncate an effective field theory, you will have ghost modes in the theory. And they are also present here in this leading order corrections to vacuum general relativity, right? So these are quadratic curvature terms. And the first one here, actually, you will see corresponds to a ghost. And many theorists argue to avoid them entirely and only construct ghost-free theories. This is a very powerful restriction, actually. In 4D, without additional degrees of freedom, Lovelock's theorem then tells you immediately that GI is essentially unique. And so even if you insist on ghost-free theories, this typically means that you have to introduce some additional degrees of freedom, which you may use for cosmology or something else. And so I would like to split between these two approaches. And then, of course, whichever approach you follow, we now get to probe such theories in these three different regimes at the level of the background space-time with black hole shadow observations, and then at the level of linearized dynamics in the in-spiral and in the ring-down phase of gravitational waves, and of course, the full nonlinear dynamics in the merger phase. And I'll try to talk a bit about all these three regimes beyond general relativity. I'll probably mostly focus on work about black hole shadows, just because of time constraints. But let's see how far we get. So let's start with black hole shadows. Now on the right here, you can already see a preview of two simulated images of rotating black holes. And I obtained these by numerical ray tracing and in the presence actually of a disk model, which is non-dynamical and simply modeled. So light is lensed, as you can see, in actually infinitely many images, starting with the n equals 0 foreground emission, which you can see here. So you somehow look a bit on top of the accretion disk of the black hole. But then you can also see the first order image, and you can see a second order and all the following up images, because the light is lensed around the black hole. And on the left, you see Kerr space-time, And on the right, you see a modified spacetime, which I will come to what that modified spacetime is. And you can immediately appreciate that differences will actually be pretty challenging to detect, right? Because they only occur, or they're only sizable in a small image region. And so theorists approach this problem typically in one of two ways. On the one hand, you may calculate spacetimes and then their shadows in specific theories beyond GR, motivated by some ideas about modified or quantum gravity. And on the other hand, you may attempt to constrain new physics just by parametrizing all possible deviations of the background geometry from GR. And since the effects will be hard to detect, we want to focus on generic effects as far as possible, but at the same time, we want to learn about fundamental physics, right? And so I think it's very timely to work in a framework that tries to bridge between these two approaches, that tries to characterize image features that arise from fundamental principles. So that's exactly what I want to do, and I will try to explain a particular set of fundamental principles and how they lead to image features that really differ qualitatively from GR predictions. And I will always focus on this, what people call the prograde, where the black hole is rotating towards the observer, the prograde image region. All right, we construct a family of spacetimes, starting actually from Kerr spacetime. And here I give Kerr spacetime in metric form and in horizon penetrating coordinates. Phi and u are the passive coordinates associated to the killing symmetries, so to axial symmetry and to stationarity. And r and theta are the active coordinates. M denotes, of course, the mass, and a the dimensionless spin parameter. So let me mention that while this metric looks very complicated, you can actually find a much simpler form by characterizing it just by about statements about the Riemann invariance. So you can make the statement that a particular type of Riemann invariant looks like this, and all the others vanish. And this is not only much simpler description, it's also coordinate independent, but it also explains lots of the mysterious properties of Kerr, actually. It relates to Carter's hidden constant of motion, and it explains the Newman-Janus algorithm, or people sometimes call it miracle, that one can obtain Kerr from Schwarzschild by a complex coordinate transformation. And so it's very useful to actually work in this way, in this description. But I'll return to the metric, which you're probably more familiar with. And the modifications that we introduce, they are restricted to upgrading the mass here to an effective mass, which depends on the spacetime. And of course, there are many other inequivalent deformations that you could perform to the Kerr metric. And choosing this particular one comes from insights from quantum gravity, in which actually we find that an effective weakening of this mass or of the gravitational force can actually lift the singularity in these spacetimes and therefore make them more consistent than they are in GR. So that brings me to the four principles that we apply. First, we demand exactly regularity of all curvature invariants. Second, we demand a Newtonian limit, just because that's observationally pretty clear. Third, we demand that the transition between these two limits is simple, by which I mean that there's only one single new physics scale. And then there's a fourth criterion, in which we demand that new physics modifications are tied to local curvature scales of Kerr spacetime. And this is a very powerful principle that we see will lead, or if you follow it or not, will determine very characteristic image features. So the first three principles, they immediately lead you to conclude that the horizon of the black hole must shrink. Regularity demands that the effective mass at the center vanishes. And the Newtonian limit demands that the mass approaches a constant value at asymptotic infinity. And then simplicity tells you that the mass has to grow monotonously between these two limits. And it's this monotonous growth that leads you to conclude that generically you end up with a more compact horizon for these geometries. And then if you add the locality principle, this is a little more difficult to explain. So bear with me for a moment. This brings me back to this complex invariant that I mentioned before. Since it's complex, it corresponds to two distinct real invariants. And so if we want to tie new physics to local curvature scales being large, we first have to define what we mean by curvature. And in effective field theory, when you would expect that whenever any curvature invariant becomes large, some corrections pop up, right? And following that, you should construct a combined invariant, which is the envelope to the maximum of all invariants. And in terms of the complex invariant of Kerr, that's really just the absolute value of that complex invariant. And you can see the explicit expression here. In any case, from this curvature scale, we can now construct an explicit mass function. And here's a representative example. On the right, it has to obey these two limits. And I plot the mass function here on the left. And the wiggly lines, the blue ones, they are the actual maximum of the invariance on Kerr spacetime. And the contours here in green, they are this constructed invariant. And you can see it approximates the actual maximum very, very well. Now, crucially, since the Kerr spacetime and the curvature of Kerr spacetime depends on the polar angle. So in particular, the curvature is largest in the equatorial plane. This also means that the corrections will depend on the polar angle. And as depicted here, this actually leads to the horizon of this new spacetime being angular dependent. And this only... Yes,
sorry, can I ask? Hi, Aaron, Sumati.
Hi, Sumati.
Hi. I just wanted to ask, I didn't understand what you mean by envelope to the maximum absolute value of all curvature invariants. I don't quite understand what that means.
Yeah, we need an envelope because if you plot just the maximum, there are zeros in the maximum. So if you plot the absolute value, there are kinks in the geometry. And of course, we don't want to have kinks in the geometry, because if you would include a non-discontinuous mass function, your geometry that you would get would have discontinuities as well. This is the only, I mean, it's really the tightest envelope that you can make. But you can think of this really just, if you go back and look at the complex invariant, it's really just the absolute value of that complex invariant. To me, that's the best way of thinking about this.
See, okay, so because you do have regular spinning black holes, you don't want to have kinks in your distribution. So
yes.
Is that, so you're smoothing, in some sense, you're smoothing it out, or?
Yes.
Something? Okay. All right.
I mean, we're smoothing out exactly here these kinks in the blue line.
All right. Thanks. Yeah.
Sure. Very good. Ask questions in between. If I don't get to the later parts, it's still better than not asking questions. That brings me now to a summary of these image features. So here you see now 3 plots that focus only on this prograde side. Left is Kerr. And then there are 2 regular black holes, one that doesn't follow this 4th principle, and one that follows the 4th principle. And so it ties to local curvature scales of Kerr. Right, before I get to image features, let me mention that effects have here been maximized in several ways. We now look edge-on onto the accretion disk. We have chosen a large spin value, and this is just to probe the space-time close to the horizon. And we also choose a slow fall-off in this mass function that I showed you to maximize effects again, and most crucially, we use a new physics scale of the order of the black hole mass scale. And vice versa, that should suggest that local Planckian new physics will be vastly suppressed, and that you will have to search for non-local effects, such as the presence or absence of an horizon, if you want to talk about local Planckian physics. You can see that resolving the n equals 1 light ring, which is this one here, or the n equals 2 light ring is what's key to start even constraining any of these features. And so resolving the n equals 2 light ring will most probably require at least one space-based telescope. And so as long as we cannot do that, we rely just on n equals 0 and n equals 1. And then we do rely on temporal variability in order to be able to remove degeneracy with unknown disk physics. And that's actually a very interesting topic for the future in the next generation Event Horizon Telescope Fundamental Physics Working Group. All right, now let's get to the actual image features. Now you can see that 2 arise just from the increased compactness of the spacetime. In both images here on the right, you can see that the shadow or the light rings actually move to the right, and therefore the whole shadow shrinks. And also the distance between these light rings is stretched out. That's just because the geometry becomes more and more compact. And then there are 2 more features which are tied to this fourth principle of locality. And I want to focus here on these cusps and dents. You see them here quite prominently in the light rings, and they're absent both for Kerr and for the regular black holes without tying to locality. And we can now understand that this is connected to what is known as circularity, and that these local models, they break circularity. And here I show the mathematical definition of circularity in terms of the Ricci tensor and the 2 killing vectors of the spacetime. But physically, you can think of circularity really just as an inversion of time and the rotation sense of the black hole. That's an inversion of the 2 killing coordinates. And in GR, sorry, yeah?
Sorry, yeah, I'm going to interrupt you just once again. I'm a little
Sure.
confused about this definition of locality that you have. If you don't mind just sort of clarifying that once again, because I don't quite understand in what sense you're starting off with a regular black hole metric, which comes from these higher derivative theories.
No. So the metrics that we're looking at don't actually come from a dynamics. This is what I was emphasizing in that it's nice because we get to parameterize background spacetimes and probe these without having to talk about a specific dynamics.
Okay, sure.
But the metric is local in the following sense, that it whenever the local curvature scales of Kerr spacetime are small, then the deviations in the new metric, in the regular metric, will be small as well. That's the demand of locality.
I see.
And that's not true for all regular black holes. Okay,
I see. All right, thank you.
Sure. Now, talking about this circularity. Now, in GR, in Kerr spacetime, it's actually crucial to use circularity to establish lots of the uniqueness theorems. And that's, I think, why lots of the literature nowadays is actually focused on circularity. But we found now, we can prove that the metrics that follow this locality criterion, they are non-circular. And this also holds for a couple of other metrics beyond general relativity and even in general relativity. And so there's really a discrepancy between these two. And it also holds that most parameterized approaches actually follow circularity. And so I think there's a gap here, and we have to be careful if we now compare two images that we don't miss these non-circular image features. And that's just something that I wanted to mention, and hopefully you'll hear more about that in the future. And with that, maybe are there more questions about this first part on black hole shadows?
I have a question here.
Sure.
So this non-circularity, what does it mean in terms of T-phi symmetry?
You mean in terms of the of reflection symmetry about the z-axis?
Yeah.
It's not immediately tied to that. So even if you have a circular black hole, you can still break the reflection symmetry.
But earlier you said that circularity, so these are the definitions, but you said you can intuitively think in terms of the T5 symmetry. You made some.
I think I don't properly know what you mean by P-phi symmetry.
T and phi.
T and phi. I see. Yeah. I'm so certainly breaking circularity implies that you will break this T5 symmetry. That's certainly true. I hope that
Thanks.
Okay, good. So let me now use the rest of my talk actually to talk a bit about a specific dynamics beyond GR, and that's this one that I put here. And I'll try to be quick on linearized dynamics and maybe say a few words about nonlinear dynamics. So here you see now this effective field theory beyond GR, and it's parameterized by two couplings of the quadratic curvature invariance. And this theory actually is known to have, even in, let's focus on spherical symmetry, it's known to have two different solutions. One of them is, again, the Schwarzschild solution, as in GR. And the other one is a branch of solutions with non-trivial Ricci tensor. And here I show now a plot of these branches with the asymptotic mass as a function of the horizon radius. And therefore, Schwarzschild is just a straight line. Now, the stability, linear stability, is known of this Schwarzschild branch. And I will get to that and explain that. But the non-Schwarzschild branch, this is what Jun Zhang and I were able to extend to, and also talk about the instability of that branch. So how to determine linear stability? There are three key ingredients. And that's, first of all, the linear degrees of freedom, so the dynamics, but then also a specific background and boundary conditions. And crucially, it's now an interplay between dynamics and background that governs stability. So now we really need to specify the dynamics. And you can write that in terms of masses of modes if you rephrase the theory in terms of the Weil tensor. And then the Ricci scalar corresponds to an additional massive spin 0, and the Weil tensor corresponds to an additional massive spin 2, which is exactly the previously mentioned ghost mode. And then you can go and put this on a spherically symmetric background and decompose into radial piece, temporal piece, and spherical harmonics, and you can separate the wave equation. And we focus on axisymmetric perturbations and focus on the lowest lying mode, which will reveal the instability. But then we can derive a single wave equation after a lot of algebra. And the potential of this wave equation now depends on the background and, of course, on the masses of the theory. And you can specify to Schwarzschild, in which case you recover known results. But crucially, we can now also study the stability beyond the Schwarzschild branch. And then you have to specify boundary conditions, purely ingoing waves at the horizon, because it's a one-way membrane, and then outgoing waves at asymptotic infinity define quasi-normal modes, and ingoing waves define bound states.
Aaron?
Yes?
This is just a reminder of last 5 minutes for the talk?
Yes, I think that should, I will make it work.
Thank you.
So let me just say that a positive imaginary part, especially in the bound state frequencies, signals a growing mode, right? And therefore signals an instability. That's exactly what we looked for. And we can first do that on the Schwarzschild branch, where you then see that there's a characteristic scale, which is known as the Gregory-Laflamme point, where the Gregory-Laflamme instability kicks in and where you have a mode with a positive imaginary part. And now we know that that's also true for the other branch, where above or below a certain mass scale of this new physics parameter, there's again a Gregory-Laflamme type instability, which means that this part of the branch is also unstable, while this part is stable. And that suggests physically that there is a lower bound on the radius of black holes in this theory. And further exploration, in particular, how this can be dynamically formed, leads me now to nonlinear dynamics. And I hope if I have 3 minutes, I can give you also a flavor of that. So in nonlinear dynamics, just as in GR, you have to evolve PDEs, and usually you have to do that numerically. And that in turn requires formulating a well-posed initial value problem. And just to make sure that everyone's on the same page, that means we look at a foliation into 3D spatial slices and a remaining time direction. And then the initial value problem corresponds to time evolution of that foliation. And it's well posed if it exists for all future time, if it's unique and depends continuously on initial data. And that's crucial to be able to do numerical simulations. Now, this has been proven in GR that it exists and it has been applied. And so then that's why we can do binary merger simulations and all these nice things with computers nowadays. Now, for quadratic gravity, that's what Hyun Lim and I are trying to redo for this beyond GR theory. And I will actually skip over a proof provided by Noakes and just tell you about the results in a spherically symmetric model. So now we restrict to spherical symmetry, and we ask whether we can simulate black hole spacetimes numerically in this theory beyond GR. And what you see here is a plot of constraint violations. So we plot the constraint, and since you add automatically numerical noise to a perfect initial condition, and we do that in a controlled way, adding more and more random noise, or less and less random noise, and you can see nicely that the theory converges. So if you would excite a numerical instability, as you would expect for ill-posed systems, then you would see that the constraint violations grow and diverge at finite time. And we don't observe that, at least in the simulation time. So it's not a proof, but it's very good evidence for that the system is well posed. And the same also happens around Schwarzschild spacetime. Again, you can nicely see that the constraint violations decrease as the noise decreases. And so at least for spherical symmetry, we are very convinced that this is a well-posed system. And that already in spherical symmetry gives us lots of interesting possibilities for future application. But the most interesting thing, I think, is to do the same thing in 3+1 dimensions. And I'll have to ask you to stay tuned for that. But we're working actually on also finding a well-posed version of this theory in 3+1 dimensions. And with that, let me conclude with saying once more that I think it's really an awesome time for theorists in GR and beyond, because we get to probe black holes, not just in GR, but in the EFT of gravity beyond GR. And with that, thanks, and please feel free to ask more questions.
Thank you. Thanks, Aaron, again for sticking to the time. Okay, we might have time for a question or two. Okay, Amitabh, please unmute and speak.
Thanks, Aaron, for the very nice talk. The metric that you showed, does that metric admits the killing tensor or killing Yano tensor?
No, it doesn't. So the metric that I was constructing for the shadows, you mean?
Well, for the separability, what I had in mind about the separability.
Yeah, but you were referring to the shadow observations, right? So these questions here, right?
Well, so, actually, my question was really about the separability. So when you separate all these equations, do you need the killing tensor for the metric?
So you were talking about the second part of the talk.
Second part, yeah.
Okay. So in spherical symmetry, it doesn't matter, right? Because in spherical symmetry, you will always be able to separate. But you're right that if you would want to go beyond spherical symmetry, and if you would want to do things analytically, you would require some form of separability. And that relates back to the first part and circularity, because actually separability is an even stronger constraint than circularity. Every separable metric that we know of is circular, but not the other way around. And so, yes, in axial symmetry, you would need, at least I don't know of a way of doing this decomposition without separability. Yeah.
Yeah, thanks.
Yeah. So,
Somati?
yeah, so I think it's in the same, the second part of your talk about the stability question. I'm a little, so you have these regimes of stability and you talk about the Gregory-Laflamme instability that arises. So
Yes.
do you, so this is the stability of the black hole system itself, right? So the Gregory-Laflamme is basically what happens to, just Kaluza-Klein space-time, and so the fact that that you
Yes.
have a Kaluza-Klein type black hole, and so it sort of splits up into beads into these pieces. So is that the kind of instability that, I mean, does this lead to some kind of a possible naked singularity, or what happens to the black hole, in other words?
It's a very good question, because it's puzzling. So as you said, the Gregory-Laflamme instability is known from higher dimensional black holes, right? If you take a 5-dimensional black hole and you compactify it, then you get that instability. And it's really funny because the wave equation that you get for the Schwarzschild background is exactly the same than you get from just GR in 5 dimensions.
Okay.
And the reason is because the spectrum, the linear spectrum, is the same. So you in both cases you get a massive spin-2 mode, and that causes the same instability. But it's a nice example of the linear dynamics actually potentially covering multiple theories, right? Because these are very different physical scenarios, like having a 5-dimensional black hole and in 4 dimensions adding higher curvature terms. And you would distinguish these at the nonlinear level, I think, but you can't distinguish them at least in spherical symmetry at the linear level. And so the wave equation for Schwarzschild is exactly the same. But I wouldn't say I'm talking here. I'm not talking about these higher dimensional black holes.
Right. So the instability here is in terms of just this growing mode. But what exactly, I mean, what do you expect physically is happening to I mean, it's in parameter space, right? So why are these lower mass MR black holes not physical? I mean, they're unstable, but what happens to them?
So my intuition is that as you start to form lower and lower asymptotic mass black holes in the Schwarzschild branch, at some point you reach the mass scale of your other degree of freedom, your ghost degree of freedom. And then as you reach that scale, you start to form a ghost condensate around the black hole. And that alters the geometry and actually pushes you into this branch where the mass, so the asymptotic, the corrections at asymptotic infinity, they still become more and more flat. But at the same time, the horizon scale grows because there's a massive spin-2 condensate forming. But this is it's really just intuition and conjecture at that point. I think we need nonlinear evolution to actually be able to make this more solid.
All right. Thank you. Thanks a lot, Aaron. It was a very good talk.
Sure, you're welcome.
Thank you.
Thanks.
Okay. Thank you. Thanks, Aaron, for a wonderful talk. In fact, thanks all the speakers. I guess Gillian left, but Anuradha and Aaron both are here. So thanks for this wonderful talks, and thanks participants for joining this late in the evening.